Hello everybody and welcome to the first in a series of lectures on electrical principles. What we're going to be looking at in this series is DC circuit theory, AC circuit theory, some semiconductor applications and circuits, and digital and analog circuits. We'll start off quite basic and build in complexity as we go along. The topic of electrical principles is quite a complex one. There's a lot in electrical theory that is very, very complex, and we might broach on this at some point, mention it in passing. But what we ideally want to do by the end of this course is have an understanding of electrical circuits to the point where we can begin to diagnose things on circuits and design our own circuits, ideally. For as long as the first humans have been on the face of this planet, we have witnessed electrical phenomena. The first and foremost of these would be lightning. This massive electrical discharge from the clouds would have been the brightest and most intense flash and accompanying roar that these early people would have experienced, leading them to attribute it to gods, and quite understandably so. Early humans also knew about the electrical properties of certain animals, such as electric eels and catfishes. The ancient Egyptians in 2750 BC wrote of the thunder of the Nile, the catfish Malapterus electricus, which they revered as the protector of fish. Mariners also knew of the phenomena of St. Elmo's fire, bright blue and purple discharges from the masts of a ship during thunderstorms, and these were generally seen as good omens by the superstitious sailors. These three phenomena, electrostatic discharge, bioelectricity, and coronal discharge as we now know them, were naturally occurring. Humanity's first experience of generating electricity were experiments with amber in ancient Greece, whereby the amber was rubbed on a soft surface and could then be used to attract small objects. This electrostatic attraction was a curiosity and remained so for thousands of years. Modern electrical theory arguably begins in the 1600s with the conceptualization of the electrical force by William Gilbert following his own experiments with amber. He published his work in the book On the Magnet and Magnetic Bodies and on That Great Magnet the Earth, where it makes the distinction between electrical attraction and magnetic attraction, which was well known at the time. From there, it is another 100 years before we begin to see the groundwork being laid out of our modern electrical theory. From the early 1700s, there have been countless electrical discoveries, with almost a new discovery every year since the 1800s. Great men wrote themselves into history with their discoveries and new technologies. Names such as Volta, Ohm, Faraday, Ampere, Henry, Coulomb, Tesla, Gauss, Hertz, Weber, a common parlance to the electrical student, whereby they're used to describe and measure aspects of electricity and electromagnetism. There are many more people that I have not mentioned. Electricity was harnessed and put to use by engineers across the world in the late 19th and early 20th centuries, and their creativity was boundless. And it is at this point, hopefully inspired by these great people, we will begin our work in electrical principles. pass. No, I'm joking. I'll give it a shot, but before I do, I just want to make you aware that if you do Google this topic, there's quite a few people on the internet that will deny the existence of the electron. They'll do it using arguments that aren't based in real life physics, but sound a lot like they do. They misunderstand the nature of the electron. They don't understand the experiments that have been undertaken to identify the properties of the electron. So they sound quite realistic, but they miss the point. So just be aware of that going forward and take a bit of caution. Make sure that if you're reading information, physics, science, check for citations, peer-reviewed journals, things like that. Wikipedia is very good in this regard because anybody can edit it, but the people that do edit it keep rigorous standards, and what you can do is go to the bottom of any article and identify the sources of said information, and then you can check those references. You can check up on those scientists that reference those papers and what papers they reference. You can go down a whole paper trail, and you'll find that multiple experiments have been done all across the world by different laboratories and different individuals, and these all point to exactly the same information. So what I'm going to try and do is talk a little bit about the properties of the electron, try and explain a little bit as to what it is from a physics point of view. We don't really need to understand it in this level of detail for this kind of level of electronics, but it's interesting and it'll give you a background as to how we obtain these quantities such as amperes or amps. And so without much further ado, let's get into it. So the electron is both a particle and a wave. Now this is quite a difficult thing to get your head around if you haven't encountered this before, but most small particles act as waves in certain situations and particles in others. We can identify the wave-like properties of the electron through diffraction experiments, where you fire them through slots and they create diffraction patterns that we'd expect to see, or we do see, in waves. They don't create patterns that we see when we fire physical particles through these slots, for example. They are particles because we can detect them discretely. So what you'll see on the screen is a photomultiplier tube. Now this is very similar to the apparatus used to detect individual electrons. What will happen is the electron will enter this end of the tube and hit the curved plates within the tube, and each time it hits this plate, it'll kick off more and more electrons. The pile of electrons at the end creates a voltage and can drive a current, and we can measure that and use it to create a pop on a speaker, for example. So you can hear these clicks each time the electron hits. So we can detect the individual electron in this manner, but we can also detect its wave-like properties. So it exists in both states, or all states. And this is kind of where this misunderstanding from other people comes from. Additionally, electrical theory operates on both kind of this concept of the flowing of electrons, but also the idea of electric fields. Now, electric fields are created by charge. A charge on an object will create an electric field around the object. We can do engineering with both this concept of the electron as a particle, but also the electric field around it. If we think about light, for example, light is a propagating electromagnetic wave that oscillates between the electric field and magnetic field, and we can create these waves by moving electrons, and this is essentially how we create radio waves. So let's look a little closer at what the electron is. The electron's a fundamental particle. It's what we call a lepton. Essentially, there's nothing that makes it up as far as we're aware. We can't divide it, we can't break it, we can't smash it, so it's just its own thing. It's essentially a point charge. We can measure the upper bounds of its radius, but we cannot actually measure its radius. And the thing is, when we get down to this level, it doesn't really matter too much, the kind of physical size of it. Its properties are more what's important. Now, I haven't really gone into explain what charge itself is, because it's an inherent property of certain particles. Electrons have charge, protons have charge, and if you smash up a proton you get quarks and they have charge as well. It's an inherent property of the universe, and we can't really explain more deeply what it is. It's just an inherent property. What we know is that charges repel. Like charges repel. Similar charges attract, so a negative charge will attract a positive charge. Two negative charges will repel. Now, in electrical circuit theory, we're not just interested in charge, we're interested in the flow of charge. But looking at the charge on an electron, it's very, very small, so it doesn't really produce any great phenomena, and if we use that charge in our equations, we'd have gigantic numbers all over the shop. So we define a unit of charge as 1 coulomb, and this is about the same charge as you get on 6.2 times 10 to the 18 electrons. Now that's 6.2 billion electrons, which is a gigantic number, but because again they're so small, we can actually measure and do things with this. And why is it that odd number? Well, we'll find out in a little bit, but it comes from the relationships with the other units. What we wanted to do is basically line everything up so we get nice numbers in all our equations, and they tie up with the previously defined mechanical properties. Now, when we've got 1 coulomb of charge moving through a circuit, so are 6.2 billion electrons flowing down a wire, for example, we call this an amp. Now, an amp is 1 coulomb per second. So the idea of current is actually a rate of change in charge with respect to time. And so it follows that the integral of current with respect to time is charge. So hopefully at this stage we can see the relationship between current and charge. 1 amp is 1 coulomb per second. So now let's start looking at voltage. Now, voltage is a measure of electrical potential, or what we describe as electrical potential, but it's quite a difficult thing to visualize. So what I'm going to try and do is go and explain it in a kind of roundabout way, and hopefully it should explain things or illustrate things a bit better. So we'll start with the joule. Now, the joule is a unit of energy, and mechanically speaking, this is equivalent to raising 100 grams, roughly 1 newton, over 1 meter. So it's roughly lifting 100 grams over a meter. Now, a volt is a joule per coulomb. So each coulomb of charge has a joule of energy if it's at 1 volt. Now, again, that's quite a hard thing to visualize, but if we've got a container like some imaginary bottle, and we start pushing electrons into it, or pushing charge into it, these charges are going to repel, they're going to try and push each other apart. So it'll become harder and harder to keep on adding more charge to the container. We see this as a voltage. So as I'm pushing charge into this container, the voltage will be increasing and increasing and increasing. And if I've done 1 joule or used 1 joule of energy to shove these electrons in this container, then that container will be raised at 1 volt compared to the original state that these, or the original place that these electrons came from. If we just abstract that a bit further, we could think of, and I don't like this analogy because it breaks down, and it breaks down quite often, but if we think of the hydraulic analogy, our voltage is essentially like a pressure, and then our current is like the flow of the fluid. As I said, I don't like that analogy, but again, it's just to try and build this idea of what a volt is. Another way of looking at it might be to think that the voltage is a number that tells you how likely that charge is to move, or how quickly it's going to move. Now, if we go back to the original derivation or original equation I gave you, we had a volt is a joule per coulomb. If we take this and multiply both sides by the charge, then we'll get voltage times our charge equals the energy in joules. Now if we look at this equation and divide both sides by time, what we'll end up with on the left side is volts times charge divided by time, and that's going to equal our energy divided by time. Now we know that a coulomb per second is an amp, so we can say the left hand side of the equation now equals volts times amps. We define power as the rate of change in energy with respect to time. So your energy expenditure over a period of time would be your power output. Now, if we raise our bag of sugar 100 grams, 1 Newton load through 1 meter, we'll expend 1 joule of energy. If we do that in 1 second, we've expended 1 watt of power. Now going back to that equation, on the left side we've got volts times amps, and on the right side we've got joules per second. A joule per second is a watt. Now what we've got is an equation that gives us our voltage times our current is our power. Now this is a really important relationship, and we'll be using it a lot to evaluate power dissipation in circuits, evaluate motor powers, and it also allows us to relate that electrical power to mechanical power. If we think about it, if we have a perfect, impossible but perfect motor, 100% efficient, and we operate this motor at 1 watt, what we'll do is we'll raise our 100 gram load, or 1 Newton load. I'll just use 100 grams because it's a nice concept, it's a nice number. We will raise that load in 1 second. So this concept of power gives us this beautiful connection between the electrical power in a circuit and mechanical powers as well. Now, the default state of any kind of electrical system, in my opinion anyway, is on fire or exploding. It's, if I take this bottle of charge and connect it to where I took that charge from, if we go back to the original or earlier example, and I take it and I just connect it directly, what we'll get is all that charge moving out that bottle instantaneously. Now what I'm going to do to illustrate this is by taking that bottle, which is a capacitor and something we'll look at in more detail later, we'll take that bottle, charge it to 300 volts, and then discharge this essentially by shorting it out, which is what I was trying to describe in a roundabout way earlier. And what we'll see is this very, very, very rapid discharge or equalization of the voltage, and it should be quite an impressive spark. Okay, so what we've got here is basically an insulated pen to charge the circuit, battery to supply the charge, a striker with an insulated handle, and then we've got the circuit itself. Now this is a camera flash from a disposable camera, and basically you put a 1.5 volt battery in, AA battery, and when you press this button, what it'll do, it'll switch through these coils here and put 330 volt on the capacitor there. So if we look up here, can I get it in focus without reflection? Possibly. Sorry about the awful footage, this camera is pretty terrible. 330 volts. So when I begin charging this end will basically be dangerous. This end, I know the voltages on these terminals here, they're going to be the battery voltage here, so I can touch this fine. So, alright, what I'll do is, this end's positive, it's marked on the circuit board there, but you can also tell by the shape of the connections there. So I'm just going to connect the battery in there. Try and get a good grip on it because I'll be holding it by hand. Now, I'm going to use the back of the pen just to apply pressure to this button here. You might not be able to see it. I'll try and come in from the side. And what we're listening for and looking for is basically there should be a high frequency charging sound. Start off low and build up. And this little LED should turn on when this is charged. Hopefully it works. We'll see how it goes. So I'm just going to press it down. Going to keep it down a sec just to make sure. Alright then, so that's charged now, I think. It's definitely in an unknown state, let's put it like that. So this end here is hot, well, not physically hot, but it's dangerous. So I'm going to keep my hands well away from that. I'm going to put a strike across these two terminals here, and hopefully we should see that spark that I was talking about, and hear the spark at least. Alright, so what I'm going to do is just connect up to one terminal and rock onto the other. That gave me a bit of a fright. Hopefully you saw that, and hopefully you heard that. I don't know if you can see it on the camera there, but can you see the little blast marks in this bit of metal here? Again, this camera's not very good. I hope you saw that spark, really do, because I don't really fancy doing it again. Maybe tilt it back. See those two bright spots on the top there? I'll take a photo of it with the digital camera in a bit, but those two bright spots, and we should see them on the terminals here. Can you see where the terminals have been eaten into? Can you perhaps see them two pits? Basically what's happened is the flow of current from here to here through this bit of metal, in order to, well, as I rotated in, whoop, little spark, yeah, as I connected and rotated it in, basically what happened is the electricity jumped the gap, and in jumping the gap, it actually evaporated a chunk of metal out there and out these. On this side here, it might have been a little local welding that I've just snapped off as I rotated it round and off there. But hopefully you can see that. It's a nice little demonstration. I wouldn't try this at home personally. Well, I am actually trying it at home, but if you're not confident in what you're doing, I've mucked about with these things before, so I'm not really too bothered. I've played with a bit of high voltage and stuff, and I know the risks, and I know to keep my fingers well away from anything on this side of the circuit or anything that's not something I know that's safe. Additionally, I've also blasted myself with one of these just across the finger, and it burnt a nice patch out the skin. Obviously it's healed, but yeah, so pretty dangerous. As I said, I really hope you saw the spark. If not, I might do another shot with a different camera zoomed in, because this webcam's a bit pants. Anyway. Okay, so as you can see, the camera was refreshing or updating as the spark happened, and so we lost the bottom of it. So here's another view of the actual thing, only without me talking over it this time and without sound. So as we saw, there was a very quick, rapid discharge of energy from that capacitor. It was enough to actually ablate or evaporate some of the metal off the striker. Now, that kind of discharge would destroy most components, or pretty much every component. So what we need to do is impede that flow of current, so the rate of change in charge with respect to time is a lot slower, and then we can control it a bit more, and that allows us to do useful things with it. So one of the ways of impeding the flow of current in a circuit is to add what we call a resistance to the circuit. Now, these resistors are essentially made up of materials that don't conduct electricity as efficiently or as effectively. If we think about electrons moving through the wire, the electrons would have more to hit into, or something like that. So it slows that change in charge with respect to time. Now, the unit of resistance is what we call an ohm, and the ohm is defined so that if we connect this across a voltage of 1 and 1 amp flows, we'll have a resistance of 1 ohm. So this gives us the relationship that the voltage equals the current times the resistance, or the resistance is the voltage divided by the current. So what we can do then is use resistors to control the flow of current within a circuit. Resistors are one of the most ubiquitous components in the whole of electronics. They exist in almost every single electronic device you will see, and they can be used for a variety of different purposes as well. They can be used to control voltages, to control currents. They can also be used to set timing values, to heat things up. They've got a whole variety of purposes. So what we're going to do now is start looking at resistors in circuits. So let's start by looking at an example. So if I have a 5-volt circuit and I connect a wire directly between the positive voltage and 0 voltage, what we'll essentially have is a zero resistance. Now if we look at V equals IR and we put in a zero resistance, what we'll essentially have is an infinite current. Now that was basically what I showed with that spark example, and this is what we call an electrical short. So what we'll do, or what we'll have to do, is connect a resistor between those two terminals to limit that current flow. So if I connect a resistor across these terminals, we'll get some current flow, and the current will flow through the resistor. And actually at this point it's worth making the distinction, or the linguistic distinction. If we think about current flows through things. So we'll have that resistor, and the current will flow through the resistor, heating it up. If we talk about voltage, the voltage will be across the resistor. So one side of the resistor will be at 5 volts, and the voltage will drop as we move through the resistor, and it will be at 0 volts on the other side. The voltage is across the resistor, not through the resistor. Voltage doesn't travel through things. Voltage always occurs across things. Current always travels through things. Now that's out the way, what we're going to do is look at these two resistors that I've got on the screen at the moment. Now these are a quite old-fashioned type of resistor. You won't see them in modern electronics, but they're very good for prototyping, for experimenting, because they're quite large. These are what we call through-hole type of resistors, and that's because they've got these long leads that push through holes in circuit boards, and then we solder those leads onto the circuit board. These particular ones are 680 ohms, and we can tell that by the banding around the resistor. These old types of resistors have these color-coded bands, and you can use charts freely available on the internet to identify the value based on these lines. Another way to do it is to connect what we call a multimeter across the terminals and measure the resistance that way. These resistors are quarter watt resistors, so they can dissipate 1/4 of a watt of power before they overheat and will fry. So let's have a look at the circuit and some maths. So what we've got is our 5 volt input. We can have a 0 volt ground line, and we just use this symbol here to represent that. And then we'll connect our 680 ohm resistor across here. And this is a 1/4 watt resistor, so it can dissipate 1/4 of a watt as heat. And what we want to do is find the current. At that current, what we want to do is find the power output, or the power dissipated. Then what we want to do, once we found all that, what we want to do is find the maximum voltage we can put on this before it burns up, and the maximum current, so the current at maximum voltage. Alright then, so we're going to be using our equations that we looked at before, and that was P equals IV and V equals IR. Okay, so we'll start on a new page. So we've got 5 volt, 680 ohm, And in order to find the current, we can use V equals IR. If we divide both sides by R, we get our current equals voltage divided by resistance. Now, I'm just going to switch out to a calculator here. I'm going to be using Octave, which is a free calculator. It's very powerful. At the moment, I'm just using it as a calculator. So 5 divided by 680, we've got 0.007 amps, or about 7 milliamps. So we've worked out our current. So that's going to equal 0.00735 amps. Okay, now what power is it dissipating? Well, we can now use P equals IV. So our power is going to equal our 5 volt times our 0.00735. Jump back to the calculator, and I'm just going to do 5 times that previous answer, and that gives us about 37 milliwatt. Okay, so what we've just done is we found our current and we found our power. So at our 5 volts, this 680 ohm resistor will have to dissipate this much power as heat. So we've just found our current and our power dissipated. Now we're going to go down and tackle these. So let's start a new page. We've got a 680 ohm resistor, and it's at 1/4 of a watt. So if we look at our P equals IV and V equals IR, well, we are looking for the voltage, so we're looking for this. We've got the power and we've got the resistance, but we don't have current. So we're going to rearrange this bottom equation here as we did previously. So I'll just take this rearrangement. I'll do voltage divided by resistance to find current. And then what we're going to do is take this and substitute it in for this current here. So doing that, we'll end up with P equals V squared over R. And then we can rearrange this because we know power, we know resistance, we're looking for voltage. So I'll multiply both sides by resistance. So I've got PR equals V squared. Then I'll take the square root of both sides. So I've got root PR equals V. Now I'm going to put that in the calculator because we know our power and our resistance. So I've got the square root of 0.25, which is our power, times our 680. And we get about 13 volts. So our voltage equals 13 volts. And what's the current at that voltage? Well, we can just look here. We know the voltage now. We know the resistance. Use this equation, V over R equals I. I'll just clear a bit of space on that side there. And we can bash that straight in the calculator now. So answer divided by the resistance gives us about 20 milliamp. Alright then. So what we've done is used these two equations, we rearranged, and we found our maximum voltage and maximum current. So we've got all this now. What we're going to do is check this experimentally. So I'm going to connect a power supply, and this is a standard lab power supply. What we've got is a readout here. For voltage, a readout here for current. We've got some adjustment knobs to set these, and some output terminals. We'll take our positive output terminal, put it through a resistor. Now, on the lab power supply that I have, these are analog gauges, and this is not accurate. You won't be able to measure milliamps on it. So we will connect this through a device called a multimeter, and this is more accurate than my power supply. So we'll connect this through, and that'll measure the current. Oh, that's where we want to be going. We'll run this experiment at 5 volts, and we'll check the current. Then what we'll do is we'll jack the voltage up, and we'll take it to 13 volts. You don't really want to be running resistors at their maximum power output, but we'll do it, and we'll probably take it over just to see what happens when you over voltage a resistor, basically put too much current through it, so it's trying to dissipate too much power. What we should see is it heats up nicely and produces some nice white smoke. So we'll do this experiment. We'll check our calculated value using the multimeter. We'll take that readout. Hopefully that should be exactly as per the calculation, so we'll be looking for about 7 milliamp. And then we'll take it over this 13 volts that we calculated here. We'll take it over that and see if it fails. Alright then, so what we've got here is the circuit as described in the previous video, on the previous section. We've got our power supply, we've got our resistor, and it's connected through the resistor, through the multimeter, back into the power supply. And this is connected on a breadboard. If we look at the underside of a breadboard, what we've got horizontally connected rails and then vertically connected rails, and these will conduct the electricity through. So as you see this connection here, it's connected across on that horizontal rail and then down here on this vertical rail. What I'm going to do is turn the power supply on to 5 volts, and I'm going to turn the multimeter on to measure that current. What we're expecting to see is the calculated current of about 7.3 milliamp. So I'm just going to turn it on here. I'll turn the ammeter on first, so I'll just rotate it round. I'm on 200 milliamp DC because it's a DC power supply, and I'm connected through the milliamp slot on the multimeter. Now I'm going to turn the power supply on, keeping my voltage down at 0, current's up at maximum because we'll get no current flow at 0 volts. What I'll do is I'll turn the voltage up, and that will take us to the 5 volts. So I've turned the power supply on now, we're at 0 volts, and I'm just going to turn it up gently to 5 volts. Now I'll try and eyeball it here. That's a little over, so that's about 5 volts, and what we can see here on the multimeter, we're at 7.2, 7.3 milliamps, well 7.2 milliamps. So this is correct as per our calculations, 680 ohms, 5 volts on the power supply. So we can validate that Ohm's law is correct. What we notice is if I turn the voltage down, it goes down linearly, and if we plotted voltage against current, we'd find the gradient of that line to be the resistance. Now what I'm going to do is I'm going to disconnect this multimeter here because the fuses were blown in it, and I'm about to stick some current through it, and I just don't want to damage the internal circuitry. So I'm going to switch it off, disconnect this cable here and plug it in where this black cable here is, and that'll give me a straight through just back to the power supply for when I over voltage this resistor. So I'm going to disconnect this, switch this off, and I can get rid of that now. Now I'm going to plug this straight in here. I'll try and keep it clear. Disconnect that one, and we'll stick it straight in here. Alright then. Now I'm just going to crank the voltage up here. So we're at 5 volts. We'll go up to 10 volts. It's probably not liking it. And now we're at 15 volts. This resistor here is going to get very, very warm, and it's still not popped, which is quite surprising. That's quite nice. So I'm just going to nudge it up a little more and see if we can fry it. So I'm at 25 volts. It's doing well for a 1/4 watt resistor. We'll crank it up a little more, nudge it up to 30. Oh, I am impressed. So it seems to be sitting there quite happily at 30 volts, which is over double what we calculated, so it's dissipating about half a watt. I imagine this will be well warm now. I'm just going to turn the voltage off, just stop it popping under my hand. Turn that right down, turn the power supply off, and I'll just feel this. Yeah, that's pretty roasty toasty. So I'll just turn it up and crank it up again, and we'll just let it overheat. It might take a minute or so. It's very impressive. Okay, so I'm going to call it quits there. It can obviously take it. That was quite impressive. I was not expecting that. Alright, so actually, not as hot as I expected. I think it must have burnt out internally, but I was hoping for some magic smoke coming out or something like that. I'm pretty sure it is well knacked. We'll put it back on and we'll see if we can measure a current through it at 5 volts again. I'll just connect it up as per before. So disconnect that one, plug that one back in, back into the multimeter. 200 milliamp. We'll see if it can actually conduct, because it might have burnt out without exploding, and we'll see if we get any current on it. So we'll just turn it up to 5 again. So that did surprisingly well. I Quite surprised by that. Alright, we'll just turn that off. Okay, so what I was hoping to show was the resistor burning up, but apparently this one can take it, which again is quite a surprise, and I'm quite impressed by that. I would not design a circuit for it to take that kind of current all the time, because it will fail when you least want it to fail. Alright then. Well, that seemed to be the little resistor that could. I was quite impressed by that. I cut the video short because it really didn't do anything after being turned on for quite a while. I imagine it would have burnt out if I left it on for a little while longer, but the video was getting boring. Okay, so I just want to make a correction on before. The gradient of that graph we saw on the previous shot, that was 1 over the resistance, not the resistance, just because of the way I drew the axes. If I switched the axes, it would have been the resistance. Alright then, so let's have a look at some problems. So, first problems on the course, what we've got a 12 volt circuit here going down to 0 volts here, and a 1k resistor connected across it. What you have to do is find the current and find the power. Well, find the current through the resistor, so through the resistor, and the power dissipated by the resistor. So that's problem 1. The next problem is, I've got a 30 ohm resistor, and I've measured the current going through it. The current going through it is 2 milliamps. What's the voltage on the circuit? How much power is the resistor dissipating? Again, 0 volts. You'll have to find the voltage here, and the power dissipated. Next problem. We've got an unknown component called component A. The component requires 3 watts to operate. It has 200 ohms of internal resistance. We need to find what voltage we need to connect across the component. Remember, we put voltage across, and what will be the current draw on this circuit. Next problem. We've got a 1/4 watt resistor. Are we within the design spec? Running this at 9 volts, will it explode? That's what we're looking for. Are we within this design spec? Is it going to handle the power? What's the maximum voltage we can put across the resistor based on it being a 1/4 watt? Next, we've got a heater, and it operates at 1 kilowatt from a 12 volt battery. So we've got basically a car battery and some kind of electric heater running from it. Find the internal resistance of this heater. How much current is flowing through it whilst it's operating? We assume it runs at 1 kilowatt whilst connected to the 12 volt battery. So we wire it directly from between the battery terminals, for example, and that generates it's a 1 kilowatt heater, so it'll generate 1 kilowatt of heat. Find the internal resistance, find how much current flows through it. And as a more difficult one, why it's in red, assuming that the previous battery discharges at 12 volt until empty, so there's no voltage drop. Typically batteries will drop voltage as they empty. We're assuming it runs constantly till it's empty, and then it instantly cuts off to 0 volts. And it's got 500,000 coulombs of charge in it. So it's got lots and lots and lots and lots of electrons in it. How long will the heater run for? Okay, so there's 5 problems. I hope you enjoyed the lecture. Have a head scratch about those, and let me know if you have any issues. Thank you very much.